right, so let's do some more examples here. So this one we're doing the lead concentration. And because of past use of leaded gasoline, the concentration of lead in soil can be associated with how close the soil is to heavily traveled roads. Now the table shows average lead concentrations in parts per million and samples taken from different distances from the road. So we can see down here in the corner lead parts per million and meters from the road. And so we're supposed to find a log model for the data. And so we're going to probably have some L of, let's call it D. That's going to be our model. So kind of lead, but LD. And then after that, we want to find an apartment complex has a dirt play area located 12 meters from a road. Calculate the lead concentration in the soil play. Well, that's going to be L of 12. And so hopefully it's going to be between 60 and 40. And then we're going to find an exponential model for the data. And then we're going to compare this model to the log model. Okay, so this is the log model. And then we're going to have an exponential model as well for L of D. Okay, so let's go ahead and start working on those. So again, as I've done, I've put the data in so it's quicker. And so now we just have to find our log model. So that's going to be number 9, and we have that's correct, so we must have did that same last time. And so this is going to be our log model, 158.574, and then minus 42.877 ln of D, if I remember right. So let's go ahead and put that in for this one. And so we had the 158.574 minus the 42.877 ln of D. And this is going to be in ppm of lead. Okay. And it's going to be, X meters or D meters from the road. So it's going to have D is going to be less than or equal to 20, but greater than or equal to 5. So D is going to be somewhere in that range for the distance. Now we want to find what is L of 12. So now we plug in 12 into that equation or function. And so we're going to take 158.574 minus 42.877 ln, and we wanted a 12 in parentheses, so 52.029. So it's going to be, again, if we plug that in, it's 158.574 minus 42.877 ln of 12. And that's going to be roughly, it's 52.029 ppm. And if we go to that, it's just going to be 52 ppm if we round to the same units. Now we have to find L of D, and we need to end the exponential form now. All right, so let's go over here and look. So we go here, stat, go over to calc, and now we want 0, the exponential regression. L1 and L2 still the same. And so now it's going to be 123.237, and then 0.932 for the other value. So let's go ahead and write that down. And that was 123 point, that's a 2, 2, I just better start over. 123.237, and then it was 0.932 to the D, and again, that's in ppm of lead, and again, 5 less than or equal to D less than or equal to 20. And now it says, which of the two models better display the end behavior? Okay, well, let's think about this. All right, so if we have a distance from the road and we have a concentration, we can see that we're decreasing concentration. And so if we think about that, how does it should look? Well, it's going to look something, the further and further away, it's probably going to get further and further out here, closer and closer to 0, right? So Will it ever go negative? Nah, we're not going to have negative concentrations of lead because that's not possible. So it's going to be something up here in the positive values. So let's plot these. Well, let's see what our, okay, so we have stat plot on. So that looks like the data points. So now let's add in our equations. And what we had was what? 158.574 minus 42.877 ln of x, if I remember. Yep. And then the other one was the 123.237 times 0.932, and that's raised to the x. And so now, graph those. All right, so now which one of those looks like it's better as far as it kind of, this one looks like it just goes, and if we probably change our window, we would see something there. Minimum, let's say -90, just for the sake of it. And maybe we should go by 20 this time instead. All right, so the blue line is starting to show these negative values. And, we talked about that they're just going to go closer to 0. And this one looks like it just kind of gets closer to 0. So if we do a trace and, well, it's not letting me go out. But it's going to keep going closer and closer to 0 there, it looks. So we need the red line. And the red line that was our exponential model. So the exponential model looks to be that's the better model. So exponential model better. Do not get negative concentrations of lead further from road. Okay, so again, we had to think about what's going to happen. Further away we get closer and closer to 0. Pretty soon, if we're 1,000 meters away, it's should be close to 0, but it's not going to be exactly 0. But that's what that should show. And the log function said, no, it's just going to come down here and it's going to be negative something, which doesn't make any sense. And so the exponential model actually was the better model in this case. All right, so now we're going to go to sleep time for women. So we've seen this kind of a thing before in one of the modules. And so I don't remember if we actually came up with the exponential model for it or what, but until women reach their mid-60s, they tend to get less sleep per night as they age. The average number of hours in excess of 8 hours. So that's a key there, in excess of 8 hours, because it's not just this function gives you the number total, it's in excess of 8 hours. So you have to take that number plus 8. That a woman sleeps per night can be modeled with that. And when the woman is between 15 and 64 years old. So now it's asking, how much sleep do women of the following ages get? 15, 20, 40, and 64. All right, so that means W is going to be that. And our sleep, and I'm going to say sleep plus 8. I'm going to have, well, actually, let's not do sleep plus 8 on the first column. Let's do sleep plus itself, and then we'll do another column and do sleep plus 8. Okay, so we're going to do 15, 20, 40, 64. So let's just plug in the values and see what we get for S. And then after that, then we can do this. All right. Using results in part A, write a model giving age as a function of input S, where S plus 8 hours is the average sleep time. All right, so let's plug these in. Let's go ahead and get out of that. Let's go over here. Now this is not cleared out, so we'll have to do that real quick. All right, and so we had the following. We had 15, 20, then we had 40, and then we had 64. And then I'm going to do like we did last time. I'm just going to plug those in to our function. And so we have 2.697 times 0.957 to the 15. And then I have 2.697 times, and oops, 697, okay, 957, and that's to the 20. And then I have the 2.697 times the 0.957 to the now 40. And then I have the 2.697 times the 0.957 to the 64. All right. So those are my values. And then basically, if we go over here to column 3, that's going to be then 9.395, and then it's going to be 9.1197, and then the next one's going to be 8.4649, and we'll have 8.1619. Okay, so those are going to be our values that we need. And so let's go ahead and write those over here. And so we had, where's my pen? 1.395, which is the 9.395. Now, if we want to, we could say that's 9 hours. And then if we take 0.395 times 60, that gives me 23.7, so roughly 24 minutes. Okay, so we can put it in hours or hours and minutes if we want to. I believe this one was 1197, so 120, I guess. And so that's going to be 9.120. And so it's going to be 9 hours, and then 0.12 times our 60. So that's 7.2. So we can say roughly 7 minutes on that one. And this one is going to be, it was the 0.465 after we rounded. So that's going to be 8.465, which is approximately 8 hours, and 0.465 times 60, 28 minutes. And then this one is going to be, it was 0.162, I believe, so 8.162, so that's approximately 8 hours. And if we do that, that's 10 minutes. Okay, so again, kind of depends on which one we want. All right, so now what we need to do is we need to do a model with the input S, where that is S plus 8 hours. And so what we're going to have then is we're going to get out the W. So we're going to have W of S is going to equal something. So now let's go back over to the other place. And so we've got our data in already. So now we just have to do the log with the current data. And so let's see here. They just want the log. So we're going to go calc. We'll do the log. Now we need L2, L1, so that's good. And we get 22.573 minus 22.752 ln of S, I believe we're using. So WS is equal to, and we had there, let me write that back to, we had written down 22.573 minus 22.752 ln of S. Okay, and that's going to be, our W is going to be years old, and that's going to be what we're going to do, and that value is going to be within the 1.395 and the 1.62. So that's going to be s is less than or equal 1.395, less than or equal to 0.162. Okay, so that's how we do that one. Let's see if we have another one here. All right, so in section 1.5, these data were modeled as an exponential function. Now what we want to do is write an appropriate model for the inverted data. All right, so what we have to do is we have to plug these in, and I'm going to pause and go plug those in real quick. All right, so I've got the data typed in as it is in the table. And what we're supposed to do is find the exponential function, which means we're going to find the inverse of what we just had here. And so to do that, we're going to have our stat. We're going to calculate. Now the inverse of the exponential is a log, so we'll do that. And because we're doing the opposite, we're going to have L2 than L1, so that looks good. And so we get 3.495 plus 10.175 ln of, and then I guess we have A, okay? So let's go ahead and put that here. So we're coming up now. We want the, let's see. All right, now let's make sure I'm doing this right. All right, so I had to write down what I was looking for. And so then we had our length of A, because now we're doing the invert, is going to be, and we have 3.495, then plus the 10.175, then we had ln of A. This is going to be in inches, okay? And so that's the inverse of the exponential model, which is what we have going that direction. And so what this is going to be is it's going to give us, the length over the ages, a less than or equal to 15, but greater than or equal to the 4, okay? So that's going to be how that one's modeled using the appropriate inverted, because initially we did the exponential straight. Now we want to write the inverted data, so it's going to be the log. All right, so I'll pause there, and I believe that's the last thing for this section.